All right. Hey, you should have finished 2 tasks already. One, finding the optimum angle to get maximum distance in projectile motion. And then also, you should have evaluated motion of a tennis ball in flight. And this was that data, okay? Now, what you see in front of me is just a little bit of an extension of what we're doing. So we're going to talk about that in just a second, okay? If we look at our data, this was the position versus time graph. A nice straight line communicates what? You guys did this in your analysis. If you remember from review, that means there's constant velocity. Now, that velocity is in the negative direction because it was headed from right to left, and to the left was negative. That's no big deal. When I go velocity, it was nice horizontal line, okay? Meaning constant velocity, okay? Now, if I look at the position versus time graph, in the y direction, if we're just looking at the y values in the data, it goes in this nice parabola, okay? Meaning, right, it is not constant velocity. That velocity is changing constantly. Now, if I used my little slope meter of my hand, my slope right now is positive at 1, and it's decreasing, right? So my velocity is steep, and then it's decreasing to 0 at the top, which makes sense because the ball in flight experiences 0 velocity vertically at the peak. And then it starts to go down, or a negative velocity, because up is positive, and it gets steeper and steeper, so it gets faster and faster, okay? And we look at the velocity versus time. I've got a positive velocity, initial, and then it gets smaller, smaller, smaller to 0. That's at the peak. And then it gets faster and faster and faster in the negative direction, which is downward. So what we've got, this is just data from a tennis ball flying in the air, but we're looking at it horizontally. We've got constant velocity, meaning once I set it in motion horizontally, there's nothing to slow it down. There's no net force on it. Now we have to assume there's no air resistance, which it looks like there isn't because it's not curved. Okay, it wasn't a windy day. But the tennis ball acting vertically does experience a force because there is acceleration. There's a negative acceleration. The slope of this line, its change of velocity over change in time, is negative, which means there's a downward acceleration of, oh, looky there, about 10 meters per second squared, which is our acceleration due to gravity. Now, I think that's pretty cool. Meaning, the ball moving left to right is constant. Once it receives the force horizontally, it stays in constant motion. But vertically, the ball is experiencing a constant force, and that force is the force of gravity, nothing else, okay? Which I think is pretty darn cool. So what I'm going to do is, let's see if I can bring this up, right? This implies, right, in the horizontal, we've got constant velocity, which means acceleration equals 0, and the only equation of motion we have is velocity equals change in x over change in time, okay? But on the other side, we've got constant acceleration. Now, this is going to be a blast from the past. We used these equations to predict how high someone went. We had someone on the blob, and they were in the air for a certain amount of time, and we were able to use the constant acceleration equations to predict how high they went. We also said if we jump from a bridge that's, say, 30 meters tall, how fast will we be going, right? So what we can do is look at two-dimensional motion separately. We can look at the horizontal, how far it goes horizontally, how fast it's going horizontally, and we can look here vertically to see how much time we're in the air. And these were those constant acceleration equations. We had v initial plus acceleration multiplied by time. I don't know if these are coming back to you. We had position final is the initial position plus initial velocity times t plus 1/2 at squared. And then we have this funny one, initial squared 2ax. Okay? These were the three equations of motions, depending on what we've got. If we've got initial velocity, final velocity, and our acceleration due to gravity, we can find out how much time we've got. If I know my initial position, my initial velocity, and some time and acceleration, I can figure out what my final velocity or final position is, and so on. So there's these three tools that we had, which was kind of cool. Okay, and we can use this concept to determine how much time we're in the air, because honestly, once you get it going, it doesn't stop in the x direction. So it goes in the x direction as long as it takes it to go up and down. And that's what this next image is going to show us. So let me pull up those equations and I'll have them posted, okay, because this will help you out for some extra credit. These were those equations, and I'll end up posting those. So constant acceleration, I'll have vertical and horizontal. These are the equations for vertical or horizontal. These are the equations for vertical, okay? That acceleration is now g, or 10 meters per second squared. Now let's get to that picture that I was showing. Now this is a different scenario. It's not the same ball, it's a different ball, okay? I've got a red one, and I've got a yellow one, and I'll put a video up there. But they're released at the same time. This one's dropped and this one shot out, right? You can see a gap right here, shot out to the right. Now what I did is I ended up drawing some lines from a consistent spot on the ball each time, vertically and horizontally, and let's see the results. Okay, so look at the yellow lines. Now of course we're going to have a distance from here to here because it accelerated, okay? But from this interval to this one, to this one, to this one. Now this photograph basically takes a picture at a constant period of time, okay? So this time interval between this ball and this ball and this ball and this ball is the same. So they're covering the same distance, right, over the same amount of time, which to me is kind of cool. So that yellow communicates horizontally that this ball is moving at a constant rate. Now vertically, I've got this pink line, okay, and it's dropping. Now this one dropping over here, right, you can see the lines get further and further and further apart, which means, right, it's accelerating. Well, so is the yellow ball. The yellow ball is also accelerating, and we're putting them side by side. Both of them are accelerating at the same rate. So even though this red ball is just being dropped and this yellow ball is being kicked out to the right, they both fall at the same time, meaning they should hit the ground at the same time, okay? And this is kind of cool. When we get into predicting motion, okay, I use my vertical motion to determine how long I'm in the air. And the amount of time that I'm in the air determines how far I can get horizontally. So my velocity vector, right, and we did this, if I had a 45-degree angle, that's my optimum angle. I'll go the farthest with a 45-degree launch. But I can figure out the velocity vector's influence vertically and the influence horizontally and find how much velocity goes horizontal and how much velocity goes vertical. I can determine how long I'm in the air vertically with these equations. So I determine my time, and then I figure out, oh, I have this much time, right? At this velocity in the x direction, I can find out how far I've gone. So I'm going to do that. I'm going to get a projectile launcher, determine its initial velocity, and then I'm going to set it at an angle, and I'm going to show a calculation, and I'm going to see if it hits the bucket, basically. Okay, I'm going to call my shot, essentially, is what I'm going to do, and we'll see if it works. Okay, I hope this helps do some explanations about two-dimensional projectile motion, what drives calculations. What we have to determine first is how much time is in the air by the y direction. Gravity dictates that. And then how far it goes by the velocity in the x direction. All right? There's a possibility that there's supposed to be a magic word at the end of this video, and I'm going to call it Grace. That's my puppy's name. All right. Oops, I woke her up. All right. See you later.